Welcome for our annual Engineering Senior Design Project Presentation Night. Our first group up is the 4 to 20 milliamp sensor interface card. The advisor is Dr. James Brooks. And without further ado, we'll invite the project to begin.
Thank you. My name is Stephen Lehman. I am on the 4 to 20 milliamp sensor interface card senior project. My teammates are Zachary Blaskowitz, Colton Young, Trevor Jeter, David Sheets, and Vincent LaRosa. The client for this project is Bechtel Plant Machinery Incorporated. Bechtel Plant Machinery Incorporated, or BPMI, is part of the Naval Nuclear Propulsion Program, or NNPP. Basically, the Naval Nuclear Propulsion Program is dedicated to developing, designing, and maintaining nuclear reactors in submarines or aircraft carriers for the United States Navy. BPMI holds a special place in that it is a private company, privately owned, but its prime and only customer is the United States Navy. The official spiel is that BPMI supports the Navy by designing and coordinating the procurement of specific components for nuclear reactors and the required support systems, and then supporting said components throughout their life cycle. In layman's terms, that means that if there is a component in a control system in a nuclear reactor in any of the United States Navy ships around the globe, BPMI has had a hand in it. Now, Bechtel Plant Machinery Incorporated uses 4 to 20 milliamp sensors frequently in their designs for maintaining and controlling nuclear reactors. So what exactly is a 4 to 20 milliamp sensor? Well, to be frank, a 4 to 20 milliamp sensor is a sensor that delivers a current between 4 milliamps and 20 milliamps. The 4 milliamps indicates a value of 0 for the sensor, or the minimum value. 20 milliamps indicates the maximum value of the sensor. These sensors can be anything. They can measure pressure, they can measure temperature, they can measure level via radar. They are very flexible. The important part of the sensor is that it's sending its data with 4 to 20 milliamps. So why exactly is this a popular industry standard? Well, to start off, if the sensor fails, then the sensor is sending out 0 milliamps. And then the people who are looking at the system know something is wrong. It's not just reading the minimum value. Other reasons that 420 milliamp sensors are industry standards is that they're very easy to configure. You simply figure out what is the maximum value and what is the minimum value, assign those to the 4 milliamp and 20 milliamp, and then everything in between. There is a simple 2-wire connection. You supply power to the sensor, and then the sensor supplies a certain amount of current. They're also highly resistant to noise and are very accurate over long transmission distances. In our project, we used 420 milliamp sensors by putting that current across a 250 ohm resistor. So the output was a voltage somewhere between 1 volt and 5 volts. So what exactly is the purpose of this project? The purpose of this project is to develop 2 different prototypes of a sensor interface card. The sensor interface card has to be able to connect to up to 15 different 4 to 20 milliamp sensors. The reason we are developing 2 prototypes is that one prototype will use a microcontroller as the brain, as the filter, as the thing that is coordinating all the different sensor data. The other prototype will use a field programmable gate array, or FPGA, to be the brains and the filter. Both prototypes have to be built to many specifications: how much power they use, how fast they respond, what configurations can they withstand, and how much outside of specifications can they handle without being damaged. You'll be hearing more about the specifications as we proceed through the project presentation. Once both of our prototypes are finished, we are to compare them and give our recommendation to BPMI. Now I'm going to hand it off to my colleague Zachary Blaskowitz, who's going to be talking a little bit about the actual system.
Yeah, so here's a look at the system overview. And the system really begins on the right side at the system controller, because this is where the user is located. And so at the beginning of operation, the user provides the configuration data and the alignment constant shown there on the right, which makes its way to the shared memory, which is then read by the microcontroller or the FPGA, which is located in the main operations block. So if we take a look at this main operations block, we'll see that this data is coming here at the bottom. But before we get to that spot, we'll see that the sensors is on the left. And this is where this is part of the sensor interface card. The sensors are attached to the card, and they are there collecting data. And so this data, once it's collected, is passed on to the analog to digital converter. And once the data leaves the analog to digital converter, it is now beyond the sensor card, and this is where it enters the microcontroller or the FPGA. And so those the data and the alignment constants mentioned earlier will help with the processing of that data. Now, this data also helps the microcontroller FPGA determine where to look for data. So there's 15 channels on this interface card, and so this data will help provide information such as what kind of sensor is located on which channel. So sensor 1, is it a temperature sensor, is it a pressure sensor? It will give it those types of data in addition to the max and minimum values, so it knows how to configure that data. And so once we get through here, once this data is processed, this data is then passed out. The final usable data is passed out back to the shared memory. And so the shared memory then is accessed by the system controller where the user is. And so now that the user can get these final values. So next here, I'm going to talk about some of the circuit design and here's a bit of an overview. So on the screen is the schematic for a single channel. So one of the 15 channels, this schematic would be repeated 15 times. And from left to right, there is the power supply, then the crowbar circuit, then the drive circuit, and then the sensor loop. And so I'll get into more detail about each one of these here in a moment, but this is kind of the main gist of what the channel looks like. And you'll see at the end of the channel, the data goes to the analog to digital converter. So starting here first with the power supply. The power supply uses a 12-volt source because as one of the specifications given to us by BPMI, we were given a 5-volt source and a 12-volt source. And so the 5-volt source is used to power the analog to digital converter in addition to the differential op amp located in the sensor loop. So the 12-volt source, however, we were told that we needed to have 28 volts for the sensor loop. And so the 12 volts is used to generate that 28 volts. And so what this power supply does is it takes this 12 volts DC, it steps it up to 28 volts DC. And so this uses a boost converter IC chip that's located at the center of the diagram here, and it steps that up to 28 volts. Now, in addition to the specifications I mentioned, there's also a ripple specification. So this power supply means a 15 millivolt peak-to-peak ripple, in addition to a 28 nominal with a 10% tolerance. And so moving on past the power supply, this output is then passed into this crowbar circuit. And so this crowbar circuit is response to another specification that requires under any single failure, the voltage to the sensors cannot exceed 34.5 volts. And so what this circuit does is it's essentially a overvoltage limiter. So the Zener diode ZD1 located at the center of the diagram is rated for 32 volts. And so if the input to this circuit, which is the output of the power supply, exceeds 32 volts, this Zener diode is tripped, which then triggers the SER on the right side of the schematic, and that will short the output to about a voltage of 1 or 2 volts. And so this will essentially stop the output from reaching the sensor loop, and so that way a voltage of 34.5 volts never reaches the sensor loop. And so moving on from the crowbar circuit is the drive circuit. And the drive circuit is essentially a switch. But before we get to that, it receives its input, like I said, from the crowbar circuit. So that is the 28 volts at the top left. But now, so to get to the switch part, the MOSFET Q1 located at the bottom can be opened or closed based off of a voltage supplied at control sig 1. And control sig 1 receives its inputs from the microcontroller FPGA. So earlier I was talking about the data that the user puts in at the system controller. This is that data about when, which channels do you want to keep active. So if this is, for example, a schematic of channel 1, if channel 1 is selected as active, then a voltage will be fed from the microcontroller through into that control sig that will then reach the gate of this MOSFET. So when this gate is opened, the 28 volts at the top can flow to ground, and you have that 28 volts across the load resistor. Otherwise, if the gate is closed, the voltage up there is left to float, and the sensor loop does not receive the voltage across that load resistor. So it's basically a switch that allows us to turn on and off the sensor loop based off whether we want to have that channel active, if we want to use that sensor, or if there's a fault, we can turn it off so we don't use excess power. So then from the drive circuit is the sensor loop. And so the sensor loop contains the differential op amp, the 250 ohm resistor, and it contains the sensor. And so on the right is the channel out header. And so the sensor would be plugged into this header. And basically there are 4 different configurations for how things can be plugged in, but the main they all act the same essentially. So the sensor can output its current across the 250 ohm resistor. Then that voltage is measured by the differential amplifier, differential op amp DOP1 shown there, and then it provides that analog signal to the analog to digital converter. Before I get to the analog to digital converter, I'm going to talk a little bit about the printed circuit board. And so what you're seeing here is a 3D rendering of a 15-channel printed circuit board design file. Unfortunately, we were not able to print out the full 15-channel circuit board, but earlier we did print a 6-channel prototype. So what you're seeing on the left is all these repeated circuits. Each of these is a channel. And so from left to right, it's the power supply, the crowbar, then the drive circuit and sensor loop, and then over off to the right of that grouping is the op amp. So then also far to the right is the analog to digital converter. And there were 3 of those on the circuit board to accommodate for all 15 channels because a analog to digital converter can do 5 channels, can handle 5 channels. And so to talk about the analog to digital converter, I will pass it over to Trevor.
So as mentioned earlier by Stephen, we have a 1 to 5 volt analog measurement taken across our sense resistor. My job was to find a way to convert this analog measurement into a 32-bit digital signal in the form of an IEEE floating point number. The part that I ordered to start with the process of this is the Texas Instrument 32-bit ADS 1262 chip. To get me started with this, I worked with an Arduino Mega, and you just used Proto Central's library and code as a starting point to pretty much troubleshoot this into trying to get it to work. After having unsuccessful testing, I ended up switching over to a 16-bit ADS 1115 to attempt to get something to work that we can work with our other testing stages. And ultimately, none of this testing was successful in the end. I was intending to move into the Raspberry Pi and have code ready for the 32-bit chip, and we never got it completely working, but we got starting points to have multiple channels supported by a chip and have the analog to digital conversion for the FPGA and the microcontroller, sorry. And now I'm going to have David talk about the shared memory. Thank you.
Thanks, Trevor. The shared memory and system controller were both left very open-ended as far as requirements, so they were designed together. This is also because they operate so closely together that the design for one flows directly into the design for the other. It is important to note that the term shared memory just needs to be somewhere for both the interface card and the system controller to save data and transmit back and forth. There were 2 main requirements for the shared memory and system controller. The first was using the 32-bit floating point IEEE standard for the data, meaning transmitting 32 bits for the data. The second was the timing requirement of updating shared memory every 50 milliseconds. This timing requirement led us to selecting inter-integrated circuit, or I2C communication protocol. This is because it is a widely known protocol, so we weren't the first ones trying to implement something like this. And also, it has a variable clock speed, which is advantageous for meeting the timing requirement. Originally, we were going to use some sort of integrated circuit, some form of I2C RAM, but then we chose to have an Arduino Uno act as the shared memory instead. This was for ease of implementation, so we could quickly get it up and running to communicate with a sensor interface card. Additionally, we are then able to use a laptop for the system controller because of the USB connection to the Arduino. This is desirable because there are endless ways to visualize and control the data for the user if the system controller is a laptop. If you look at the figure, you can see an overview of the flow of data for this part of the design, starting with the user at the system controller on the left and flowing through the design. As you can see, we also needed a bidirectional logic level converter in between the shared memory and the interface card. This is because the high voltage for the Arduino is 5 volts and the high for the interface card is 3.3 volts. So this integrated circuit rectifies that mismatch. I2C protocol works by sending messages in 1-byte packages. For those of you playing along at home, 1 byte is 8 bits. A single transmission can be multiple packages long, but all the bits being sent are sectioned into those 1-byte packages. Because of this, we need a data message protocol between the two devices on the I2C bus so that the devices know what information the bits correspond to. This table shows the call and response between the interface card and the shared memory. The interface card is what's called the master on the I2C bus, so it does all of the work, and the shared memory is called the slave, so it just responds to the master's request. I'm not going to go into detail about the entire protocol, but in the first section, during configuration, the interface card sends a message requesting to know some part of the configuration data, and then the shared memory sends a message back giving that information. Then, when the card is collecting data, it sends 5 bytes in a single transmission, where the first byte corresponds to the actual sensor data. And so those 4 bytes are each 8 bits, and you get the 32-bit meeting the specification. This protocol works well and is flexible so that if any other data needs to be transmitted, it can be added to the protocol. Next, since we are using a laptop for the system controller, we can send data to and from the Arduino using USB. As we'll see on the next slide, our design does this by utilizing 2 programs. The one for uploading the configuration file is called CoolTerm, and it has the ability to send a text file through the USB connection to the Arduino. The configuration text file contains all the data needed upon startup, and a portion of an example text file is seen in a picture on the next slide. Can I get the next slide? Maybe my screen might be behind. So the design also uses a program called Telemetry Viewer, which helps visualize incoming comma-separated values, or CSVs, from the serial port. So for our design, the shared memory sends sensor data to the laptop in the form of CSVs. Then Telemetry Viewer can be configured to display the incoming data in various ways. There's also a picture in the bottom right of an example setup of how the user can configure the program to view the data. We chose to use this program because it can show the data just about any way the user would want to. So on the top right, you can see an example of the configuration file. It's a text file. And then in the bottom right, you can see an example setup for Telemetry Viewer, where the user can view and control the data. Next up, Vince is going to talk about the microcontroller portion of our design.
All right, thanks. As David said, I will be talking about the microcontroller unit, or MCU, portion of our project. Colton and I were the MCU programmers, with Colton dealing with focusing on mainly the shared memory portion and making a connection between the MCU and shared memory, and myself focusing on self-testing, data organization, and the filtering of the data. So looking at this filter, you can see that there are 2 main components here, which is the shared memory and the microcontroller unit, with one key piece of information being passed in between them, which is the configuration file. So this configuration file is going to consist of 5 to 6 different pieces of information, which are the number of sensors connected, each sensor's type, each sensor's minimum detectable range value, each sensor's maximum detectable range value, and whether the user wishes to self-test or collect data. And then if the user wishes to self-test, a 6th piece of information is going to be passed, which is going to be dealing with self-testing. So with this, there are going to be with those 2 options that the user gets to pick, we are now going to start focusing on the self-testing portion of the code. So self-testing, as you can imagine, is going to deal with testing the circuit that we have and the sensors that are connected to it. So to do this, each sensor is going to be tested in between 3 different ranges: 0 to 20% of their readable range, 40 to 60% of their readable range, and 80 to 100% of their readable range. So to do this test, a value from the user is sent to both the circuit and the MCU, so each knows how many volts are or should be applied to each sensor. Next, because the MCU knows each sensor's range, it is able to calculate the value that the sensor should be returning, and then it will compare that value against the actual data. So this comparison is going to tell us whether or not the specific sensor is performing correctly for each range. Switching gears, we can now focus on the collection data portion of the MCU. So the collection of data is going to have three main components. First is the organization of the data itself. The organization of the data goes into each sensor will have a list that corresponds to that sensor itself. Now, a list is what Python uses, but you may know it as a vector if you've done any other type of programming. So they're essentially the same thing. And because one of these specs requires us to have 15 different sensors all hooked up at once at max capacity, it made coding this organization rather complicated at times to be able to get things organized correctly. Next, the average, there's a running average taken of all the data for each sensor, and it will return that data so that the user can know all the history or the history of the average of what's happening with that sensor itself. Lastly, a filter is put on the data that will be returning a calculation of the average of the last 5 data pieces for each sensor. And this is just to give the user a better idea of what's happening most recent when it's coming to data collection, because they might be expecting a certain data type, and the average of these different pieces of data will give them a better understanding of what's happening. Lastly, those 3 things will be sent to the shared memory unit using I2C, and this loop will continue endlessly until the user decides to end the program. So now I'll be passing it off to Stephen to talk about the FPGA.
Thank you, Vince. So as we can see in this next slide, there is a block. We have the block diagram of the code for the FPGA. Now, as you can see, there is an active sensor vector, and then there is raw data vectors and filtered data vectors. Every sensor that is active is going to have a raw data vector and a filtered data vector. But there's only going to be one active sensor vector and one final vector. So first off, vector is not necessarily a common term in coding. It is something that is used in the coding language VHDL. Now, to talk about VHDL, I kind of have to talk about what FPGA actually is. FPGA is a field programmable gate array. It is a solution. It is a solution to problems that uses its hardware instead of lines of code. The field programmable gate array is a bunch of gates, logic gates, that when programmed in a particular way, the hardware is aligned so that it can simultaneously execute many different operations at once. When you program an FPGA, you usually use a language like VHDL. The difference between VHDL and a lot of other programming language is that it simultaneously uses its lines of code. It doesn't execute its lines of code in order 1, 2, 3. It executes 1, 2, and 3 at the same time. So this piece of hardware and this coding language are very good for handling many channels at once, something which is very important for this system. So the actual bare bones of the code are that after the sensors have been configured, we save a vector or a list of binary data that holds which sensors are being used and which ones are not. This data vector of active sensors helps the analog to digital converter not waste its time sending data from sensors that are not being used. This data is sent into a 32-bit long raw data vector, which is then filtered through a running average filter, very similar to the running average filter that Vince was talking about. So once all this data is collected from each active sensor and filtered, it is then combined into one long final data vector and sent out. This final data vector is every single filtered data vector linked together. Then it is sent out using I2C to the shared memory. Now, the FPGA code does not have the capability to self-test. That is something that we were not able to achieve and would be a good next step for another team who is taking up this project. So that covers the code of the actual system. Now to talk about the actual physical enclosure of the system is my colleague Colton.
Okay, hello everyone. Yeah, I'm gonna talk about the enclosure I designed. So the main goal of the enclosure was to make it easily transportable, which meant it had to be compact. So the overall dimensions are 22 inches long by 10 inches wide by 4¼ inches tall, which is just big enough to fit the PCB in the bottom layer. And as you can see in the two figures, the enclosure is designed to have 3 different layers: a top, middle, and bottom. The top layer is a lid to keep debris from getting in and affecting the components that are in the middle and bottom layer. So the middle layer is where the Raspberry Pi, Arduino, and FPGA are mounted. The layer has cutouts in its walls for connecting to the 3 components that are inside for power, or if you need to hook the Raspberry Pi up to a screen, you can plug in HDMI or anything like that. It also has 4 cutouts in its floor for routing wires from the PCB in the bottom layer to the components in the middle layer. And then going to the bottom layer where the PCB is mounted, there are 20 ports that are cut out in the wall of the bottom layer. 15 of those ports are for connecting sensors to the PCB, and the other 5 are for test jacks and supplying power to the PCB. Along with that, there are 4 tabs in the middle layer that insert into the bottom layer to keep everything from moving around. And the top layer acts as a lid and sits on top. Next, I'll talk about the budget. So looking at our budget, we spent a total of $541.50. The diagram shown is a Pareto diagram, which helps us look at how much money we spent in certain areas on the project and what percent of that makes up our total spending. So looking at that, as you can see, our biggest 3 costs were the microcontroller, PCB, and FPGA. They make up 2/3 of our total spending. This makes sense though, because they make up the bulk of the project and are where we spent most of our time. So a couple places where we actually able to save money were the shared memory. So in the shared memory, the team decided to use Arduino Unos, which David had talked about previously, for ease of use and for ease of hooking computers up to use as the system controller. It also saved us a lot of money, because if we would have had to go out and purchase Arduino Unos, it would have cost us around $45 to buy 2 of them, which doesn't seem like a whole lot, but that would have been a 300% increase in the money we spent on the shared memory, which was very nice to already have had those. So another place where we were able to save money were we use pseudo sensors, which we made in-house using potentiometers, which are used to mimic real sensors instead of having to buy them. And if the team would have had to go out and buy 15 sensors to test the whole project, we could have easily spent over $500. And next, I'll talk about the future work. So going forward, we weren't able to finish up everything. So some things that we definitely would like to work on in the future, or another team, would be going back and testing all the things we designed to make sure they're up to BPMI's specifications. Also, we never were able to test the whole project from start to finish hooked up in one piece. It was testing each component separate. So it'd be nice to see it start to finish work properly, and then to determine whether the FPGA or microcontroller would work better for this application. And then questions. Any questions?
Thank you, team. What I'd like to do is explain how we'll run the Q&A. First of all, just keep your question slide up there, and we'll keep that up there as a placeholder until the next team transitions in with their first slide, which would be, in probably about 10 minutes. Also, as I said, I don't know if I just said that, but I'll say it again. Going forward, the future groups, if you can only transmit the video of the person that's talking. Originally, we were going to have all of the team members with video live. That seems to be an issue for people with somewhat limited bandwidth. So let's just try going forward. The person that's talking is going to go live with the mic, live with the video, and everyone else just go live with your video when your time comes up, okay? For the questions, if you can just text me if you have a question. This is from professors, from faculty advisors, from visitors, students as well. Just text me, and then I can call on you, and then you can ask your question.
Mark, you might want to ask your guests simply to turn on their mic to be able to ask a question. That's what we're doing on the other channel.
Okay, that might work better. So if you have a question, forget about texting. Just share it on your mic by activating your mic and asking your question. I have a question while we're waiting on that. I was moving in and out of the room, and apologize if I missed this, but can you put this in context of the overall cost and how this would fit into the market if you were looking at a need for this kind of device? What kind of industries or applications you could use this kind of interface card for?
Yeah, so this card was primarily designed for Bechtel plant machinery. So it's really a custom design for the specifications that they've given us. And they actually gave us a document that was around, I think, 26 or 28 pages with specifications, things that they wanted for applications for their purposes. So I suppose it could be marketed for other applications, but it's really specified for their needs, especially with regards to need for 15 channels, things like that. One of the good parts about having a 420 sensor is because one of the highlights of that was they have good they're resistant to noise, but they also retain accuracy over long transmission distances. And so when used on a naval warship or a ship, of great size, it's important to have that transmission distance because the sensors will be located, well, not necessarily be located next to where the card's going to be seated. So that's one highlight for kind of why they want that type of specification.
Yeah, thank you. Yeah, what I was getting at, I think you've addressed that partially, is maybe by changing the specs slightly, you might be able to apply this to other industries because using amperage to transmit sensor data is a pretty old technique, and it's pretty commonly used in situations where you have high transmission distances. We have a question from Aaron. Aaron, go ahead and ask your question.
Yes. How does your hardware and enclosure get rid of excess heat?
So one thing with that, this is Colton who talked about it. One thing with that, going forward, we would have to design that. Originally, there was actually holes cut in the lid so that it would let heat escape out the top, but it wasn't. It wouldn't allow me to do that in the design, and it was kind of toward the end with designing it, so I wasn't able to implement that. But going forward, there would be like holes cut in the top to allow heat out of it.
So here's a question, because if I understood correctly, the analog to digital converters never worked right, neither one. And how far did you get with that? And do you have any idea what the problems were?
So with the 32-bit chip, what I had done is we actually got a surfboard for the chip and put it onto a breadboard, and I put the components on myself and then used an already designed code from ProtoCentral to attempt to test this chip. And my testing ended up being unsuccessful in the fact that it was just saying that I had 0 volts all the time. And so there was clearly an error in the hardware or software. And so I think that would be close to being implemented. And then obviously I had plans for the code to change and make new functions and actually redesign the code as a whole and into Raspberry Pi. As for the 16-bit chip, it was kind of right before we left campus that we had decided to start looking into using that as a intermediate step, I guess I could say. And we never really ended up implementing that at all. It was more so just a plan that we had. But it was already on a board that had the hardware components attached to the board. And so all that needed to be done with that was actually design code for that as well, and then test it. And I had the number of bits and how to initialize each of the chips set up, but we never ended up successfully testing those.
Thank you. There's a question from Dr. Bright. Mike, go ahead and ask your question so everyone can hear that.
Sure. So if you guys had successfully completed the project and had a working FPGA and a working microcontroller option, how were you going to test those, and what criteria were you going to use to determine the best approach?
So I think I could take this one. BPMI was kind of vague about what particular criteria better was meant. So as far, we obviously had to meet certain specifications, but both of the prototypes have to meet certain specifications. In my opinion, of course, I invite any of my other team members to come in and correct me, but we would probably test accuracy. How accurate is the sensor reading? How quickly does it handle the data? Especially as we add more and more sensors, can it handle multiple sensors changing rapidly? Or is there going to be a little bit of data lag? Again, heat would be a good question that we just didn't get far enough in the question. Does one of them really get really warm? So yeah, we didn't quite get to that didn't quite get to that part in the project, but we were thinking about that.
Thank you. Dr. Rumbaugh, please state your question.
Yeah, thanks, guys. I was wondering if the I2C connection worked well with the level shifter and everything.
Yeah, I can answer that. We did a lot of testing. Like I did a lot by myself with like 2 Arduinos at the beginning to get a grasp of how I2C works and whatnot. And so then we were also able to test with the Arduino and the Raspberry Pi. And we were able to test like a good bit of that with the logic level converter. But we weren't able to get it like fully functioning. We did have some issues with the speed, but it was having more issues without the logic level converter, obviously. So when we got that, we were able to get it to function pretty well, but we weren't able to like fully test it. So it's hard to know like if it was like 100% the right design choice, but it worked pretty well from what we were able to test.
Thank you.
I had a general, any other questions? If not, I had a general question. This is more of a project management question. This has been a very unusual semester, obviously, and I was wondering how your group handled not the technical work, but just the management change from being on campus, having access to labs, being access to faculty, especially your advisor in person, to doing all this online using a pretty powerful collaborative tool, but still a virtual tool nonetheless. I was just wondering how your group handled that, and what were some of the challenges, and what are some of the things that went well?
I think I got this one. So get on my camera here. So one of our main issues was sometimes using Git as a whole. It worked very well early when we were all around each other and we could know when we were actually pushing and pulling our code or whether it was our documentation. Once we got home, it kind of went by the wayside, and toward the end here, working on the presentation and some of the other documentation that has to be done, got rather difficult with Git problems that were occurring. As a whole, most of us were kind of separate on our different sections, so there didn't have to be too much communication between like the different parts, because we had made those connections pretty well before we left, so that went kind of seamlessly. It worked out very well. I think that was pretty much it. And we still maintained very good communication though along the way. If we were changing things in our design and during our stand-ups, we were able to talk with Dr. Brooks a lot about what we were doing and how we could improve it. And if we were having issues, we were able to keep that communication with him, and he was able to talk with us about it.
Okay, thank you. Thank you, Sensor Interface Card, for being our first group for this season, and thank you for all of your efforts. You certainly have our virtual applause and our congratulations for now finishing your senior year under certainly some very challenging circumstances.